So now I am recording it.
Yes,
I think there will be no problem.
Yes.
Okay. So initially, we have to write down, that is, why do we study? So these are the few things. Number one, common distribution. Many natural phenomena and statistical data sets exhibit a normal distribution. Therefore, understanding the properties of the normal distribution allows us to analyze and make predictions about a wide range of phenomena. So that is one reason. Second reason is the central limit theorem. The normal distribution plays a central role in the central limit theorem, which states that the sum or average of a large number of independent and identically distributed random variables tends to follow a normal distribution, regardless of the underlying distribution of the individual variables. So that is the central limit theorem. So we have to understand what is called the central limit theorem. Another important reason is the statistical inference. The normal distribution is used extensively in statistical inference, which involves making predictions or drawing conclusions about a population based on a sample of data. Many statistical tests, such as the t-test, ANOVA, assume that the data are normally distributed. Okay.
Yes, sir.
Next is another reason, that is the descriptive statistics. The normal distribution is often used as a benchmark for describing other distribution. For example, we can use measures such as skewness and kurtosis to compare the shape of a distribution to that of a normal distribution. Overall, studying the normal probability curve allows us to better understand the behavior of random variables, make predictions about real-world phenomena, and perform statistical analysis on data. So like that, we have to write down, that is, why do we study? The second point is the history. So normal distribution was introduced by the French mathematician Abraham de Moivre in 1733. He used it to approximate probabilities associated with binomial random variables when n is large. This was later extended by Laplace to the so-called CLT, which is one of the most important results in probability. Then I have given some picture. Then Carl Friedrich Gauss in 1809 used the normal distribution to solve the important statistical problem of combining observations, because Gauss played such a prominent role in determining the usefulness of the normal probability distribution. The normal probability distribution is often called the Gaussian distribution. Gauss and Laplace noticed that measurement errors tend to follow a bell-shaped curve, a normal probability distribution. Okay, Professor.
Yes,
so
sir.
Here another important thing, that is after reading
Yes, sir.
Paragraph, okay, we have to write some MCQ.
Okay, sir. Fine, sir.
That is vital.
Okay, sir.
Next is the central limit theorem. I have discussed the central limit theorem here. The central limit theorem is a fundamental concept in statistics that describes the behavior of the means of a large number of independent and identically distributed random variables. In simple terms, the central limit theorem states that as the sample size of a random variable increases, the distribution of the sample means will approach a normal distribution, regardless of the underlying distribution of the original variable. For example, let's say we have a population of people with different heights. If we take a random sample of 100 people and calculate the mean height, it may not necessarily follow a normal distribution. However, as we continue to take more and more samples of 100 people, the distribution of the sample means will start to look more and more like a normal distribution. The center limit theorem is important because it allows us to make the inference about a population based on a sample, even we don't know the underlying distribution of the population. It is used extensively in statistical inference, hypothesis testing, and confidence interval estimation. Another important issue is the measurement errors in normal curve. Measurement error refers to the discrepancy between the true value of a variable and the value that is measured or observed. In the context of a normal probability curve, measurement error can be visualized as the difference between the true score of a subject on a continuous variable, such as height, weight, or IQ, and the score that is recorded due to imperfect measurement instruments or methods. Measurement error can have several sources, such as limitations in the precision of the measurement instruments, differences in the interpretation of instructions or questions, and variability in the conditions under which measurements are taken. These sources can contribute to random error, which is a type of measurement error that affects individual observations and causes them to deviate from the true score in a random manner. The errors are normally distributed with a mean of 0 and a standard deviation. The normal probability curve is systematic and bell-shaped, with most errors clustering around the mean and fewer errors occurring at the tails of the distribution. This is clear?
Yes, sir.
Now I am writing the characteristics of normal probability curve.
Okay.
First one is the symmetry. The curve is symmetric about its mean, which is also its peak. If we were to take a large number of samples from a population and plot the values of these samples on a graph, we would find that the majority of the values cluster around the mean. Second one, peak location. The peak is found at the location of the mean. As we move away from the mean, the probability density of the curve decreases, resulting in a lower likelihood of observing values further away from the mean. Number 3, unimodality. It indicates that the majority of observation or measurement in the population or sample are clustered around the mean, with fewer observation occurring in values further away from the mean. Number 4, bell-shaped. So we have to ask the students why it is bell-shaped and why it is called unimodal. So this type of question should be there.
Okay, sir.
Bell-shaped. The curve is bell-shaped with the tails asymptotically approaching the x-axis as they extend further from the mean. The bell shape of the normal probability curve is a result of the center limit theory, which states that the sum or average of a large number of independent and identically distributed random variables approaches in a normal distribution, regardless of the underlying distribution of the individual variables. This means that many real-world phenomena, such as human height or IQ, can be modeled as normal distributions because they are the result of multiple independent factors that contribute additively to the final outcome. Next is the asymptotic. The curve approaches but never touches the x-axis as it extends to infinity in both directions. Number 6, area under the curve. The total area under the curve is equal to 1. Is equal. Measuring that the probability in any possible event occurring is 1. Number 7, central tendency. Location of central tendency is at the middle point of the curve and it is 0. Standard deviation. The standard deviation is a measure of how much the data deviates from the mean or average. In a normal distribution, about 68% of the data falls within one standard deviation of the mean. About 95% of the data falls within 2 standard deviation of the mean. And about 99.7% of the data falls within 3 standard deviations of the mean. This is known as the empirical rule or the 68, 95, 97, 99.7 rule. Next is the skewness. Skewness is a measure of asymmetry of the probability distribution. In a normal probability curve, the distribution is symmetric.
Professor, I'm interrupting. I have a class. Shall I?
Oh, sure.
Okay.
Thank you, madam. Thank you, madam. I think this is okay, no, madam?
Yeah, this is okay. I've been listening. In fact, I need to learn statistics all over again.
The more we study, the more we learn.
Yes, sir.
Thank you.
Okay,
Madam.
thank you.
Yes, sir. Please continue, sir.
Next is the skewness. Skewness is a measure of asymmetry of the probability distribution. In a normal probability curve, the distribution is symmetric, meaning that it is equally likely to have values that are above or below the mean, and the curve is centered around the mean. Therefore, the skewness of a normal probability curve is 0. Next is quartile. Quartile, in a normal distribution, the first quartile is located at a z-score of 0.67. Okay.
Right, sir.
The second quartile is located at a z-score of 0, and the third quartile is located as the z-score of 0.67. First one is the minus, and second one is the plus.
Yes, sir.
Because that is the first quartile.
Yes, sir.
Less than 0. So this is the normal probability curve distribution. After that, I have written the applications.
Yes, sir.
I want more elaboration. This one.
Okay, sir.
The normal probability curve and its characteristics have numerous practical uses in various fields. Some of which are statistical inference. The normal distribution is widely used in statistical inference, such as hypothesis testing and confidence interval estimation. It is used to model the sampling distribution of many statistics, such as the mean and standard deviation. Quality control. The normal distribution is used in quality control to identify defects in products and process. It is used to model the distribution of measurements and to set tolerance limits. Okay. So I think this is related to your area.
Yes, sir.
So if there is any specialist in quality control, their study can be adequate.
Yes, sir. That upper control limit and lower control limit, national tolerance limits, UNTL, LNTL, so that can be included here.
Okay. Next is the financial analysis. The normal distribution is used in finance to model the distribution of stock returns and to calculate probabilities of future stock prices. Medical research. The normal distribution is used in medical research to model the distribution of many physiological measurements such as blood pressure, heart rate, and body temperature in 2016. Yeah, that is one study.
Yes, sir.
Next one is the educational testing. The normal distribution is used in educational testing to model the distribution of test score and to set grading curves. Psychometrics, the normal distribution used in psychometrics to model the distribution of psychological traits and to set cutoff score for psychological test. Risk analysis, the normal distribution is used in risk analysis to model the distribution of losses and to calculate probabilities of extreme events such as natural disaster and financial crisis. Next is the estimation. So here I have given some data.
Okay, sir.
And this is the art studio.
Okay, sir.
So based upon that data, I have calculated the confidence interval, etc.
Okay. Yes,
So
sir.
this is the approach I have followed.
Sure, sir. Sure. Very nice, sir. Very
Now you tell me,
extensive
sir.
approach.
Yes. Now you tell me in which way you can help me. And
Yes, sir.
after that, skewness, kurtosis, area estimation,
Okay.
that will be made. So now you tell me that is in which way ABBS can provide support.
Sir, definitely, sir. Like you have created a file for normal probability distribution. Like that, we'll also take up some topics in the total thing, and we'll give some kind of a sample to you. Like suppose if I just take a hypothesis testing, and I'll just follow the same approach like you have started with the topic introduction, then you have mentioned history, then you have given the characteristics of that particular topic, then you have given application areas and examples along with figures. We will also try to create like hypothesis testing or some one topic like that, and I'll share that with you. You can just go through that and you can share your feedback. Like, is it according to your expectation, or anything should be added, or anything should be modified, something like that. So if you are okay with the sample topics, then we can take up the total content and we can just give that content to user.
Okay, sir. Now, so this is my need.
Okay.
That is skewness, kurtosis, and area estimation. These three are left.
1 minute, sir.
So
one is skewness, kurtosis, okay,
and area estimation.
Area estimation. Okay, sir. So these three.
If you can work on these three,
Okay.
Then that will be that will help me a lot. Number one.
Definitely, sir.
And number two,
Yes,
there are some of the applications there,
okay.
not the characteristics.
Okay.
Applications, specifically the
Yes,
quality control, financial analysis,
Yes, sir.
and risk analysis.
Financial analysis, risk analysis, and quality control.
Quality control.
Yes, sir.
Okay. So these three are very much related to the business area.
Yes, sir.
Okay.
Yes,
So
sir.
if you can elaborate this part
Okay.
with some example or anything,
Right,
so
sir.
that will help me a lot.
Definitely, sir. And
Okay.
so
Another thing,
Yes,
yes.
sir.
Another thing. So when you will write, you have to follow the same format, similar format. Okay.
fine, sir. Yes, sir.
I think in this way we can grow our work.
Definitely, sir. And here you have used only R output. So we
R.
need not have Excel outputs at regarding
No,
this.
Excel output is possible if you can give
Okay.
any support, that is the Excel, SPSS, definitely.
Sure, sir. So then what I do is, today is Friday. By next Tuesday, I'll share the content related to skewness in the format which you have given. Like I'll follow the same skeleton as well as structure, and I'll share the topic skewness with you. Like what is skewness, what is history, like who started that concept, the characteristics of the curve, like what is left skew, right skew, positive, negative, something like that, and application areas, examples, and how we can get the sample output in either R as well as Excel. So based on your feedback, I'll start the next topic, like courtesies, estimation of area, quality control, all these things. Is that fine, sir?
Okay, no problem. But
Yes, sir.
if you can add something about the application of skewness in business data
Definitely,
analysis.
definitely, sir. I'll add that. Like I'll follow the total skeleton structure as how you have shown to me. I'll follow all the concepts and I'll give that to you, sir.
Okay.
And one more doubt which I got here is, sir, this data we have, I think some of the things which we have typed on our own and some data which we have.
No, this is a hypothetical data.
Okay, so hypothetical data and
it is a simple hypothetical data. I have not used any my own data.
Okay.
It is a simple hypothetical data.
Yes, sir.
Therefore, you can find out the significant difference there or not.
Okay.
So that is the hypothetical data.
Fine, sir. And in addition to that, you have
studio
mentioned...
is there. No? So if I can write down any hypothetical data and do the analysis, I get the result. So no
yes,
problem.
sir. Yes, sir. And here you have shown some historical facts like Gaussian.
That should be that should be that
from
is
the web source. From the web sources. Okay, sir. Okay. And probably I'll include the sources or the links of this content also at the end.
Yeah,
like from where we got this details about Laplace, Gauss, something like that.
Yeah.
Then fine, sir. I'll just give a sample document to you by Tuesday. You can have a look and you can just give the feedback so that we can proceed further, sir.
Okay. Thank you.
Fine, sir. So thanks a lot, sir. Thank you very much for your support in these things.
Thank you, sir. Thank you.
Fine, sir. Sir, will it be possible to share this document? Because I have seen in my WhatsApp, even I did not get that one. Will it be possible to share this?
Okay, sure. I will send you. Achha, sir, can you arrange your time tomorrow at 8 p.m.
Tomorrow
at night
8 p.m.
Online, because tomorrow there will be one course inauguration.
Okay.
That is mental health infographics.
Sure, sir. Sure, sir. How much time will it take, sir, from 8 p.m. to? 8
p.m. to 9 p.m.
Definitely, sir.
So
I'll be there.
That will be the inauguration. So
sure, sir.
If I can invite you to say few words, then you will say something. I think that is possible.
Definitely, sir. No problem, sir. No problem at all.
So
please
you give me your give me your JPEG picture.
Okay.
And your small biodata so that we can introduce.
Sure, sir. I'll mail you, sir. I'll mail you, sir.
Okay. Thank you.
Okay. Thanks, sir. Thank you, sir.
And please tell it to Madam.
Yes, sir. I'll share that to Madam.
Yeah,
also, sir. Okay,
because
sir.
I have invited you.
Okay, sir. Okay, sir. Thanks a lot, sir. Thank you, sir. Yes, sir.
I'm closing now.
Yeah, thank you, sir. Thank you, sir. Bye, sir.